Hello everyone. Today we will be just going through derivation of load vector due to uniformly distributed load, and this is also known as traction force also. Due to traction, derivation is also same, and load vector due to uniformly distributed load is also same. And this figure whatever is there, this shows the beam element having two nodes 1 and 2, and here there is a uniformly distributed load which is acting, and this quantity is nothing but P naught Newton per meter is the quantity of UDL which is applied on this beam. And at node 1 you can see here the displacement at node 1 is V1 and theta 1, and at node 2 the displacement is V2 and theta 2. Okay. Where V is the displacement that is in y direction and theta is rotation. Now we will see the derivation here. Here load vector due to uniformly distributed load. To find out this load vector, first we will be writing the work potential equation. This already we have seen in the previous classes also. Work potential due to uniformly distributed load is given by Wp is equal to integration of P naught V dx, where P naught is that uniformly distributed load and V is nothing but the displacement in y direction. And you can see here V is nothing but h into q. H is Hermite shape function and q is the displacement vector. And you can see here what is h? H is nothing but h1, h2. For h2 we write Le by 2, h3, and for h4 also we write Le by 2. And what is q? Q is nothing but a nodal displacement vector, where v1 theta 1, v2 theta 2. These two are for node 1, these two are for node 2. And work potential equation becomes P naught, where we replace V by H into Q dx. Again similarly what we will be doing here is H, whatever the shape functions are there, they are in terms of zeta. That is why we replace dx by d zeta, that is dx is equal to Le by 2 d zeta. Now work potential equation becomes integration for this length of an element Le, P naught Le by 2 HQ d zeta. Now what we will be doing is we'll take out Q outside and we just integrate for this term, that is P naught Le by 2 H into d zeta, and this we term this as load vector. For that we use symbol as TE. We also call this as load vector due to traction or load vector due to uniformly distributed load. Now the next step is again a same process, where we will be substituting the values of h, nothing but the shape function. Shape function h is nothing but h1 Le by 2 h2 h3 Le by 2 h4. P naught Le by 2 is a constant, we take it outside and we are just going to integrate this shape function terms with respect to d zeta. So now we substitute the values of h1, h2, h3 and h4. These are already known now. What is h1 written here? H2 is this, h3 is this, h4 is this. P naught Le by 2 we have taken it outside. Now we need to integrate all these terms one by one, and after integrating we need to put the limits -1 to +1. Why -1 to +1? Again it is zeta. For this beam element it varies from -1 to +1. Now after that we are going to integrate these inside terms. So what we will be getting here, just see here, just compare this equation. 2 is there. If you integrate 2, it will be 2 zeta. With respect to zeta we are integrating, and next minus 3 zeta becomes 3 zeta square by 2, and 1 by 4 whatever is there I have kept it common outside. Similarly I will integrate this, and here also for h2 also Le by 2 I will be keeping it outside, and 1 by 4 I will take outside, so LE by 8 it becomes. Again integrate this, 1 becomes zeta, minus zeta becomes zeta square by 2, minus zeta square becomes zeta cube by 3, plus zeta cube becomes zeta 4 by 4. This is about the second. Third one becomes 1 by 4, I have taken it outside, so 2 becomes 2 zeta, plus 3 becomes 3 zeta becomes 3 zeta square by 2, minus zeta cube becomes minus zeta raised to 4 by 4. And last term for H4, LE by 2, again it is 4 I will take outside, so LE by 8 it becomes, into inside the bracket I will write the integration of this. Minus 1 becomes minus zeta square by 2, zeta square becomes zeta cube by 3, zeta cube becomes, after integrating, zeta 4 by 4. This is what we have got after integrating. Now we will be substituting the limits minus 1 to plus 1. After substituting the limits, I will keep this as it is. Inside here I will substitute the limits. So limits is plus 1 minus 1, substitute here plus 1 minus 1, what you will be getting, check here also you will be getting, here you will be getting 0, and here also you will be getting 0. So here if you substitute, you will be getting 2 into 2, it will be 4. Similarly here also substitute minus plus 1 first, next is minus 1, check 1 by 1. Here you will be getting 2, where there is zeta, limits from plus 1 to minus 1 will be getting 2. Here it will be 0, again plus 1 means 2 by 3 you will be getting 0. Similarly here also, if there is a zeta here, then it will be 1 plus 1. Means what is the reason you are getting 1 plus 1 is 1 you are substituted, minus of minus 1 will be plus 1. That is why you got 1 plus 1 here. So here you will be getting 0, here also you will be getting 0 here. Similarly here if you see zeta, there is a zeta means 1, minus of minus 1 is plus 1, so minus of 1 plus 1 will be minus 2. Here it will be 0. Again similarly here also 1 plus 1 by 3 plus 0. So this is the equation where we have substituted all the limits, that is plus 1 and minus 1 in this equation. So after substituting, what you will be getting here, you can see here. So if I simplify this, what you will be getting is 4 cancels. So left out is P naught LE by 2. Here is the P naught LE by 2, where we have taken the traction equation. T is equal to, or the load vector due to uniformly distributed load. So similarly here also P naught LE becomes LE square by 12 you will be getting here. If you simplify this, you will be getting this. Again simplify this, you will be getting P naught 4 cancels. So what is left out is P naught LE by 2. Similarly here LE into LE becomes LE square minus P naught LE square by 12. If you simplify, again it will be 12. So this is the final load vector equation when there is a uniformly distributed load. So how you are going to represent these values here? So here is first term V1, and the second will be which one? V1 theta 1, V2 theta 2. So here it will be V1 theta 1, V2 theta 2. V1 and theta 1 are for node 1, V2 and theta 2 are for node 2. So this is how the load vectors are distributed on the beam element. Similarly, the derivation of this is not that much required actually. That is why you just remember this equation straight away. Load vectors for uniformly varying load is, if it is of this side, from left to right, if it is varying from maximum to minimum, then the equation will be like this. If the UVL, that is uniformly varying load, if it is varying from left to right, minimum to maximum, means from 0 to maximum, then the equation will be this much. Means this is the load vector if it is uniformly varying load. If the load of variation of the load is different, then the equation will be different. From left to right, if it is from maximum to 0, and from left to right if it is 0 to maximum, then the equations will be like this, where P naught will be negative here and P naught will be negative here and here also both. Thank you.